The acidity or basicity of a substance is measured by the pH scale. The concept of pH was first introduced by Danish chemist Søren Peter Lauritz Sorensen at the Carlsberg Laboratory in 1909. It is unknown what the exact definition of P stands for. Some references suggest that P stands for power, others refer to the German word potens, meaning power in German. Still, others refer to potential. Jens Norby published a paper in 2000 arguing that P is a constant and stands for negative logarithm, which has also been used in other works. H stands for hydrogen. Sorensen suggested the notation pH for convenience, standing for power of hydrogen, using the logarithm of the concentration of hydrogen ions in solution. Although this definition has been superseded, pH can be measured if an electrode is calibrated with solution of known hydrogen ion concentration. Pure water is said to be neutral. The pH for pure water at 25 degrees Celsius is close to 7.0. Solutions with a pH of less than 7 are said to be acidic, and solutions with a pH greater than 7 are said to be basic or alkaline. pH measurements are important in medicine, biology, chemistry, food science, environmental science, oceanography, and many other applications. An acid is traditionally considered any chemical compound that, when dissolved in water, gives a solution with a pH greater than in pure water, for example, a pH less than 7.0. Some of the strongest acids are fluoroantimonic acid, HFSB F5, superacid, FSO3HSBF5, carborane superacid, HCHB11Cl11, fluorosulfuric acid, FSO3H, trifluoric acid, CF3SO3H. Acids are generally sour in taste. For example, the sour taste of lemon juice is due to citric acid. Stronger concentrated acids or their fumes often produce a stinging feeling on mucous membranes. They change the color of pH indicators as follows. They turn litmus paper blue and methyl orange red, and they turn phenolphthalein colorless. They react with metals to produce a metal salt and hydrogen. They react with metal carbonates to produce water, CO2, and a salt. They react with metal hydroxides and metal oxides to produce water and a salt. They conduct electricity, and depending on the degree of dissociation in aqueous solution, produce solvonium ions such as hydronium H3O+ ions in water. A base is most commonly thought of as a chemical compound that, when dissolved in water, gives a solution with a pH greater than 7. Examples of bases are sodium hydroxide and ammonia. Examples of strong bases are potassium hydroxide, KOH, barium hydroxide, BaOH2, cesium hydroxide, CSOH, sodium hydroxide, NaOH, strontium hydroxide, SrOH2. Bases feel slimy or soapy on fingers. Concentrated or strong bases are corrosive on organic matter and react violently with acids. Bases turn litmus paper blue and phenolphthalein pink. Strong acids and bases such as hydrochloric acid, nitric acid, sodium hydroxide, potassium hydroxide are employed both in analytical stages and as hydrolyzing agents, preserving agents, dilutants, and solutions pH stabilizers. Such substances expose the personnel to the following occupational risks: fires, outbursts, and explosions. In fact, many compounds are volatile and easily flammable. Irritations and caustic injuries, chemical burns. Acids and bases, but also some salts, have a noxious power which varies in strength with the tissue these substances come in contact with. Acute intoxications. Extremely powerful poisons such as cyanide, arsenic, mercury compounds, animal and vegetal toxins may be found in the laboratories. Intoxication may occur as a result of accidental indigestion, inhalation, or less frequently as a result of skin contact or inoculation. Are acids and bases sustainable? The answer is yes, they are. There are a wide variety of acids and bases, and there's no way we can possibly use them all up.